Welcome back to part 2 of Onshape4FTC. My name is Jay. I'm on Team Wirecats FTC number 14864, and today we're going to go over FTC setup for Onshape and mechanical basics. So, before we start, Game Manual 0 is a great resource if you're new to FTC or just need a refresher. I recommend reading this in full and then coming to this video, because then you'll have a much better understanding of what I'm talking about. So, the first part of mechanical is fasteners. So, to fasten means to join things together. So, in robotics, you'll often be using screws to do this. There are many types of screws. The ones up here are just the most common ones that you will mostly see. So, a socket head screw has this cylindrical shape up top. A button head screw is kind of like a socket head screw, but the head is much thinner, so it can fit in smaller spaces. A countersunk screw has this angled head, which means that you can recess it into a plate or something and it can be flush with the surface. A grub or set screw doesn't have a head at all. The drive or the Allen bit that you use to turn the screw is inside the screw, so the head doesn't take up any space. And then the last most common one is the hex cap screw. This one you can tighten with a wrench or a hex driver, but your driver will go around the outside of the head instead of having a drive on the inside like the rest of these. So, the way a screw works is it has these cylindrical markings called threads. So, the screw itself has male threads, and whatever it's screwing into will have female threads. So, these screws, so if you look at this diagram, this screw has a male thread, and this nut has a female thread. So when you screw it together, the male and female threads can join and fasten. Moving on to nuts, there's a hex nut and then a lock nut. A hex nut is kind of like a lock nut, but it's a lot simpler. You'll see that on the inside is the female thread, and you just screw a screw into it, and it'll tighten. Now, a lock nut is like the hex nut, except you'll see there's this little blue ring on top. What this blue ring actually is, it's a little nylon insert, so when you screw in, the heat from you screwing in the screw will melt this nylon, and the screw will set inside of the nylon. So what this does is whenever motors and actuators are moving around, your robot will have a lot of vibrations. The nylon insert just stops your screws from loosening over time to these vibrations. If you have to use a hex nut for whatever reason, you should always be using lock nuts, but if you have to use a hex nut, use blue thread locker, and this pretty much serves kind of like a lock nut. It'll lock the thread into place. So, types of drives, there's a bunch of drives, but the Phillips head, slotted or flat head, an unslotted hex drive, or just a socket or Allen drive, those four are the most common drives you'll see. And a drive is like the screwdriver or bit that you use at the top of the screw to screw it in. So if you look over here, we have socket drives on most of these, and then the last hex cap screw is a hex drive. Now we're on to motion basics. The most important part of any motion is a ball bearing. So if you look at this ball bearing, you'll see there's an inner circle, an outer circle, and then little steel balls separating the two. So the way a ball bearing works is these balls can rotate smoothly, and they space out the outside from the inside. So pretty much, if I was to hold the outside ring still, the balls would allow the inside ring to move very smoothly. On the right here is another type of ball bearing, and you'll see this one has a little lip on the outside. This one is called a flanged bearing. This lip is the flange, and this is helpful if you want to mount your bearing somewhere. The flange can stop your bearing from falling out. Now, shafts. So, to actually put your bearings on things, you need shafts. Shafts are pretty much metal rods that you mount things to, and these will be used for transferring power from one place to another. So in FTC, I recommend sticking to hex shafting, specifically GoBuilder's hex shafting. GoBuilder's motion system and structure system is just really nice to work with, but these concepts can apply to almost any build system. So if you look at this stainless steel rec shafting, you'll see it's like a hexagon shape, and this hexagon can fit perfectly inside our ball bearing from up here. And what this means is if I hold this shaft still and put a bearing on it, I can spin the bearing freely. Now, the bearing can still slide left and right, so what you need to do is stop it from doing that. with these things. There's two types of collars, a clamping collar and a set screw collar. On the clamping collar, the screw right here screws into the other side, and it's not actually screwing onto the shaft. So it'll join the two sides of the collar together to tighten it around the shaft. A set screw collar, this little set screw right here, will screw into the shaft, and it will hold by pushing itself into the shaft. Generally, you always want to use clamping collars, and you always want to Loctite or thread lock any of the screws that you use, because your shafts will be rotating very fast and it will have lots of vibrations. Set screw collars still have the advantage of being thinner and less bulky compared to clamping collars, since the grub screw that it has to fit is a lot smaller. Couplers are used to join multiple shafts together. So let's say I have a shaft and it's not long enough. What you can do is you can insert the end of that shaft into this coupler, and then insert another shaft into the other end, and then tighten down the screws, and the coupler will clamp around both shafts and effectively join them. Standoffs and spacers. Let's start with a spacer. A spacer is exactly what the name says. It's a spacer. It creates space. So you'll see on the inside of this one right here, there's no threads, which means you can't really screw a screw into it, but you can pass a screw through it. And this will pretty much just create space. Now, a standoff is a spacer, except it has threads. So if you look at the other three right here, these all, you can see the circular threads on the inside, which means you can screw into it from both ends and tighten it. A spacer will just make space, while you can thread into a standoff. A hub is the main thing you use to attach other components onto your shaft. So if you look at this specifically is a Sonic hub from GoBuilda. So if you put this hub onto your shaft and then tighten it, the hub will rotate with the shaft, and then you can mount whatever you want onto these screw holes. And this hub is also clamping and not set screw, so that's another benefit. That's the basics of motion, and if you want more information, you can look at the Game Manual 0. Next up is power transmission. So in FTC, you will almost always have to get power from one place to another. So power will come from your actuators. If you look at the next slide, for example, motors and servos, these will give you power. Now, to get power from the output shaft to other areas, you will need to use power transmission. So one way of transmitting power is with gears. Gears have little teeth that mesh with other gears to transfer power. So as, for example, as this little one moves, it moves the big one because the teeth mesh. With gears, you can also create ratios, gear ratios. For example, because this gear right here is smaller than this big one, this small gear will have to spin multiple times for this big one to spin once. So you can use that to increase speed, increase torque, or whatever gear ratio you need. So pulleys and timing belts go hand in hand. The timing belt is a piece of rubber or fiberglass that has these little notches called teeth, and these notches fit into pulleys. So when the pulley rotates, if you look at the example belt run right here, you'll see the notches are in the pulleys. So as one pulley rotates, if this pulley rotates, it'll rotate the belt with it and rotate the other pulley. So timing belts are really nice at going longer distances, because if you would look at something like this, if you had to transfer power from this pulley to this pulley, but you had to use gears, you would need either very, very big gears or a bunch of gears. So belts are really useful over long runs. Sprockets and chain are like belts, but most of the time they're heavier duty because the chain will usually be metal. So the sprocket is kind of like a gear, but it's a lot thinner, since the teeth lock into the chain as the chain spins. Chain is also nice because you can change the length by adding or removing chain links, while on a timing belt, if you're buying closed loop timing belts, you're locked into this size. So sprockets and chain might be good for prototyping, but for more efficient power transmission, timing belts and pulleys are usually better. Now, if you don't want to transfer power, you can do something called direct drive, where your motor directly powers whatever it is it needs to power. So for example, I could directly mount a wheel onto the output shaft. However, this isn't recommended if you don't really know what you're doing, or if you don't support the motor well, because if you direct drive something, any load that gets put onto that thing that you're direct driving will get distributed into the motor, and it could break the motor over time. electronics. So there's two main types of actuators in FTC. One of them is motors and the other is servos. So if we look at the left here, you'll see this is a motor. If we look at the Go Build a Motor, which is the preferred motor type in FTC, although Rev Ultraplanetaries are also nice sometimes, this motor right here is called a bear motor, and this is the base of many other motors in FTC. This motor right here has a 1/8 inch D shaft and spins at 6,000 RPM. Now, if you look at the one on the left, what GoBuilder has done, if you ignore the red circled part right now, you'll see that the bottom portion of this motor is the exact same as this bear motor. So what GoBuilder does is they take a gearbox and put it on that 6,000 RPM motor to manipulate its RPM, so they can reduce speed and increase torque by putting a gearbox on. And their planetary gearboxes also help distribute load a lot better, since this bear motor shaft can break very easily. So GoBuilder puts a gearbox onto the bear motor, and they get this output shaft that's a lot easier to work with. Now, motors are usually for high power applications, such as driving around, running linear slides, or anything of that sort. In contrast, you have servos. Servos are usually used for much lower power actuation, such as, for example, if you had a claw, you might want to use a servo to open and close that claw. Now, the downside of servos is that they're much easier to break than a motor with the gearbox on it. So, because the servo is so small, the internal gears can break very easily. So whenever you're using a servo, if we go back to power transmission, you want to avoid direct driving the servo. To mount things onto a servo, you can use attachments such as this servo hub. You'll see that the little spline on the inside here can connect to this part of the servo, and then you can screw it down. But you should always avoid direct driving whenever possible. You should use belts, gears, or anything of the sort to take load off the servo. You can even support the output with the bearing. This GoBuilder servo does pretty well in most cases. There's also 3 different speed options. Most common FTC servos will follow around the same specifications as this one, but if you have extra money to spend, or if you're looking for something with a lot higher power, you can get these expensive Axon servos, or alternatives include Swift Robotics servos, or Amazon has DS servos. Just make sure that they are all competition legal, but servos generally are used for much lower power applications than what a motor would be used for. So a servo generally has low RPM and comparatively lower torque a servo usually has lower RPM and lower torque than a motor. So now let's actually start setting up Onshape to use an FTC. So luckily Onshape already has a pre-existing part library with parts from many common vendors in FTC, so you don't have to import parts to CAD with them. So you can either download the extension that I'll link in the description. All of these will be linked in the description, or you can email first@ptc.com to be directly added to the library. I'll show you the difference in a second, but if we click on the link, you'll see this FTC insert tool. What you can go ahead and do is hit this subscribe. It's free, so we'll hit get for free. Okay, and now we have this insert tool. So if we go back here, let's get some feature scripts. So in Onshape, a feature is like, for example, extrude. In the last video where we extruded parts, that was a feature. Onshape has the ability for users to add their own features. So if we click over here, you'll see someone has written all this code for us to use this feature. So up here we can hit plus custom features, then we can click Lighten. This Lighten will now be a feature that we can use. Alright, moving on. So after the Lighten feature script, we can go ahead and add the Vent, Spur Gear, and GearLab feature scripts, just like we added the Lighten feature script. I'll speed this part up. Okay, now that we have our feature scripts, we can move on to number 6, which is BeltGen, PulleyGen, SpacerGen, ScrewGen. So the next 4 are all generators that give you commonly used parts that you can configure to match your specifications. So this is a really handy timing belt generator. I didn't create this. This was from Team Looney Squad. So what we can do, we can make a copy and just put it in this folder, and we'll just make a copy just so we always have it for use, so we don't have to use this link every time. Okay, now we have our own copy. So let's keep going. So let's do the same for the PulleyGen, the SpacerGen, and the ScrewGen. Now we've added those four. The last two on this list are Suslib and SimplifiedParts. So these are like the other documents that we added, in the sense that you'll see there's like configuration options on this left side we can change, but these just have a lot more stuff. For example, this one specifically has things like gears, sprockets, screws, nuts, standoffs. So this one is like the other ones, but it just has many more parts that you can customize. So this is also very helpful. So I'll just make a copy of this too. And lastly comes simplified parts. And again, this is a collection of multiple different parts. So we'll make a copy of this too. And what simplified parts lets you do is, if you're running on a lower end computer, these parts have a lot of the key details removed from them, so it's a lot easier for Onshape to regenerate them. So if you're on a lower end computer, this might help you, or just in general, if you're making something where a part might not be visible, you want to save some computing resources, you could use simplified parts instead of actual full scale parts. Now we've managed to get all of these 11 key features and documents and parts. So these are just now always going to be in your Onshape if you ever need to make parts, like for example timing belts, pulleys, gears. If you ever need to import screws. So these are just nice tools to always have. Now let's make a new document. So this is part 2 of the tutorial, so we'll just name it part 2 for example. Okay, now we have a fresh document, and if we go to the assembly part, right, so up till now we've only been working in the part studio, but now we can start moving into the assembly. So what we added in the app store, number 1 right here, the FTC parts library, you'll see it pop up in this right hand column as insert tool. Now when you hit insert tool, it'll open up a menu. You see this window, it's asking you to authorize, so we'll just hit yes on that. And then now we have access to the FTC parts library, so I'll hit home, and now you can find parts by going to global libraries. Under this you'll see all these different vendors. So for example, let's say I want to go build a part, so you can go to go build a. You can go, for example, let's say I want a motor, I can go to motion, I can find motors, I can find, let's say I want this 5204 series motor, so there's configuration, so let's say I want the 435 RPM version, so I'll just click on that, and then I'll just get this. Now you'll see that we've imported that motor for use, so now we can assemble with this motor. Now if you chose the second option, emailed first@ptc.com, I find that after a couple of days they'll respond to you, and I find that the library that this gives you, although it's technically the same as this one, it's just a lot smoother to work with in Onshape. So if I close the insert tool, if you email it, the one you'll get added to will pop up under this insert button. So you can go to other documents, FTC Robotics part users, and you'll notice as this one runs a lot smoother. So for example, motion, if you want to get that same motor, it would go 5204, and then the motor is an assembly, so I'd go to assemblies, I would hit, for example, 435 RPM, and then in this one you can actually move it around before you add it in, and you can add in multiple different things, and then you can hit confirm or cancel. So if I hit cancel, it'll go away. If I hit restore, it'll come back. So now you have these motors in your assembly. So what you can do, you can click and drag to move things around. Now, the cool thing about Onshape is that motion actually works. So let's say I want to lock this motor's position, but I want to see the shaft move. What I can do is I can click on a part that's not going to be moving. So I know that this jacket of the motor shouldn't be moving. So for example, just for testing purpose right now, I'll right click and hit fix, and fix will stop it from moving around. But now what you'll see is that you can take the shaft and it actually works. So now let's go back to the insert. Let's go add, for example, let's go find a sonic hub. Motion, hubs, sonic hubs, 16mm pattern, and then we're looking for the 8mm Rex bore, which is right here. We'll add that. Alright, now we have a sonic hub. Now if you want to attach this sonic hub to this, what Onshape has are things called mates. So up here you'll see a fasten mate, a revolute mate, a slider mate, planer mate, cylindrical, pin slot, ball slot, and parallel. And there's a bunch of other tools here, but the main ones you're going to be using are fastened and revolute. So what a fasten mate does is exactly what it sounds like. It fastens two things together, it joins them. So what I can do, I can click fasten mate, or I can hit the keyboard shortcut M. Okay, now this will pop up this window, and over here I can change the mate type if I want to. So I could change it to the other options, but I'll keep it as fasten. So mate connectors. Every part in Onshape has a bunch of mate connectors. So if I hover over this sonic hub, you'll see all these white little dots show up. These are all mate connectors that I could possibly choose. Like I can go around the edges, and anytime you see that little yellow circle with the red, green, and blue lines on it, that means right now you're hovering over that mate connector. So what mate connectors are, it defines the points that you want to mate. So for example, if I was to click this one over here, this mate connector right here, whatever it would join to this exact point, right? But for a sonic hub, we want to connect it to the middle of the shaft. So we'll take the middle, and you'll see that it might be difficult to get to that middle because every time I try to go over, I go into empty space. So what you can do is you can find where that mate connector is available, and then you can hold your shift key, and now you'll see that empty space won't make the mate connectors go away. So now I can actually find it, and I can click it. Alright, now you'll see I have the mate connector selected, so whatever I mate will go connect to this exact center point. Okay, now I want to put that on the center of this motor. So if I was to choose something like a corner, let me just show you what would happen. If I chose this one right here, you'll see that it'll fasten to the corner. But what we want to do is put it to the middle. So what I can do is cancel this. I can go back over here, choose that mate connector again, and let's say to get the middle I find this. Oh, but I can't reach the middle, so I can hover over here, and you'll see that the middle circle is, right now it's highlighted, like you'll see the yellow circle, which means if I click right now it'll work, but I can also hold shift and then go to the actual connector and click. But you could also just hover on the outside and click. Okay, so now you'll see my sonic hub is perfectly in the center of the shaft, and now because I fastened them, they're joined together. When they're joined together, they move as one. So if I grab the sonic hub and I start rotating it, you'll see it moves with the shaft. So let's now look at a revolute mate. So let's say I have my sonic hub, and let's say I add in a screw, for example. So actually our screws will be owned by me, because if you remember all these copies that we made, so we have one called configurable screws. So let's say, yeah, this is a fine default screw, so we can use this. And then if you see this mate connector, if that's kind of in the way, if you don't like looking at that, you can click on it and it'll highlight this one, for example, in the left bar, so you can go down and then you'll see mate connector, and you can hit this hide button to get rid of it. Okay, so now if I was to hit M to fasten mate, and I fasten this screw into this screw hole, you'll see that sometimes it flips and goes upside down. So to change that, what I can do, I can hit flip primary axis. And flip primary axis will flip the side that it mates to, and then secondary axis is like primary axis, but it'll just rotate it by 90 degrees. So you can do that, you can combine the two and get the right rotation. Okay, but if I hit the check mark, now it's mated and these two move as one. But let's say, for example, I use a revolute mate instead of a fasten mate. A revolute mate will revolve, it'll revolute. So let's choose this mate connector for the bottom of the screw. Let's revolute mate it to this right here, and then again it's flipped, so I'll use the flip axis button to move it to the other side. And now you'll see this screw is revolute, so it's not fastened anymore. On first glance it looks fastened, but now if I do fix if I right click on the Sonic Hub and fix it into place, the Sonic Hub can't move. Because this was revolute mated, it can spin. So we'll go over more assembly tips in the future, but for now, that's all you need to know about mates. Now let's start playing around with some bearings. So let's say I go to Go Builder, let's say I find some shafts. Shafting and tubing, and then if we scroll down and find the configurable ones, so let's just say I'm using some stainless steel shaft, why not? And I'll change the length, let's say I want this much. I can add this shaft in, and I don't like that mate connector there, it's kind of in the way, so I'll just click it, go over here and hide it. Okay, so now I have the shaft. Let's say I want to put a ball bearing on that shaft. So I'll go back into the Robotics part users library, I'll go to Go Builder, I'll go to Motion, I'll find bearings, ball bearings, flanged ball bearings, then we'll use this one. So it won't be in Part Studios, it will be in Assemblies because the bearing as a whole is an assembled piece. So now we have our bearing in here. Let's say I mate that bearing. Let's say I fasten the inside of that bearing, because if you think about it, the shaft will go on the inside of the bearing. So when we're joining them, we'll use the inside. So I'll choose that part, that mate connector, and then I'll hold shift to go to the middle. I'll mate it to the middle, and then right now it's off the shaft, so I'm going to use the flip to flip it to the other side. Alright, perfect. Now my bearing is on my shaft. So if I just fix the shaft into place for now, you'll see that I'm able to move the outside of this bearing, and the inside stays locked around the shaft. This is the basics of how a ball bearing works. Okay, but the thing is, if this was real life, there'd be nothing holding the bearing from moving left to right. Like if I delete my mate, in real life, I could move this bearing right off the shaft. There's nothing holding it in place. So when you CAD, you want to make sure you constrain your bearings and stop them from falling out. So on this side, what we could do, well, we have these threads right here. So we could just grab a screw and put the screw there. So let's go to Insert. Let's go to Owned by Me. And this time, instead of taking it from the screws document, just for practice, let's take it from the configurable parts document. So you'll see all of these different things. Let's say we just want a screw, and these look like some pretty good configuration. So let's do that. Okay. So let's try mating this. Let's see what happens. So I mate this, and then I mate it into here. Okay, so it flipped backwards. So again, let's just use the flip primary axis and just flip it. Now let's hit the confirm. Alright, so you'll see now we have a screw. But if you look, there's still a gap between the screw and the bearing part. So technically this bearing could still slide out. So this isn't the type of screw we want. Right, so let's right click this screw, change its configuration, and instead of a socket head, let's use a button head. And the button head screw will have a larger and flatter head, so you'll see it change in real time. And if we hit confirm, okay, now this button head screw, let's do the same thing. Let's mate it to here. That's much better. So now this bearing can't come out because you'll see there's a little overlap between this part right here and the inner part of the bearing. So now this bearing can no longer fall out in real life. On the other side though, the bearing can still slide rightward, this way. So what we need to do, we need to stop that too. So how, you may ask, let's use a collar. So again, we'll go into FTC parts, we'll go into the part library, go build a motion, we'll find collars, and we'll look for the collar we want. So we want the 8mm Rex clamping collar. So the 8mm Rex clamping collar, it's right over here. Okay, so we can use this collar right here, and now what we can do, we can mate it. So I want that middle piece again, so I'm going to hold shift, I'll mate the middle of this to, let's say we made it directly to the bearing, like this. Actually, let's use the other side. So you'll see there's this little lip. I'll explain what that little lip does on this side, but you'll see the other side is flat. So let's say we use the flat side just as an example. So I used the flat side and I made it to the bearing, and then I flip it backwards like that. Okay, and then if in real life I was to tighten the screw down, this circle bit would be clamped around this hex shaft and it wouldn't be able to move anywhere. And because this one wouldn't be able to move, the bearing is now stuck. It can't go left because of the screw, and it can't go right. So this is a properly constrained bearing. However, there's one thing wrong with this. So let's see if you can figure it out. The thing that's wrong is that in a ball bearing, the outer and inner parts spin independently of each other, right? But right now what we've done with this collar, the collar is rubbing against the inner and outer parts. We don't want that to happen. So that's what this little lip right here is for. If we mate with the front side instead of that side, you'll see that now what this little lip does is, I'll take a section view, so I'll right click and hit section view just so you can see it better. You'll see what that little lip does is that lip only hits the inner part of the bearing. The lip stops before it hits the outer part. So the bearing is no longer scraping because that little circle lip only touches the inner race. So anytime you have bearings, you want to make sure you're not hitting both races at the same time. You want to make sure you're only hitting one of the bearing races, because that way you'll have smooth motion. So let me right click and turn off my section view now. And you'll see that this bearing now can still spin freely in Onshape because we haven't done anything to mess with its rotation. We just mated these two pieces to either side and constrained it. So those are the basics on how to set up Onshape for FTC. Now you have all your parts, so I recommend you go practice and mess around with a bunch of parts. You could look at the Go Build the websites, you could explore the other folders in the parts library, just try to put together some basic motion systems. Next episode we'll do our first real robot CAD. We'll actually start CADing. What we'll do is we'll make a drivetrain, a simple 4 mechanism wheel drivetrain. So that's something to look forward to. So remember, just read up on Game Manual 0, gm0.org. I'll link everything in the description. Thank you for watching. If you think you learned something, please consider subscribing. It's completely free, and stay tuned for the next part.